Today is Sunday, November 7th. It's about 4 o'clock in the afternoon, and this was daylight savings time, so everybody's hopefully feeling a little bit more rested with the extra hour of sleep. So we are talking about exam 4. So to remind you, exam 4 is in about 6 days. It is going to be on Saturday. Where's my drawing tool? There we go. So your exam is on Saturday, November 13th at 10 a.m. And you guys will remember that we open that window at 10 a.m. and we close that window at 10:30. So you just need to be in there at 10 a.m. sharp. So 10 a.m. as close to 10 a.m. as possible. It covers 3 different chapters, but only a very small part of the 3rd one. So it is going to cover chapter 8. There's 2 sections in chapter 8 that we never talked about. So y'all might not have noticed that we left them out, but maybe you did. So there are 2 sections. There's one is 8.2. 8.2 is really interesting. If you were ever interested in forensic analysis, 8.2 actually talks about how you can take a sample of something and figure out its empirical formula by burning it in oxygen. So it is actually really interesting. The thing is that that particular calculation can be a little bit tricky. And honestly, it takes me about 20 minutes to walk through that particular calculation. And why do that exact calculation when instead we could do something more generic that applies to a lot of different reactions? So 8.2 is not covered and it's not tested on. But it actually is pretty interesting if you're interested in forensics. So I do recommend that you check that one out. 8.5 is also actually pretty interesting. It talks about chemical reactions in particular families. The reason why we don't test on 8.5 is because it essentially winds up being a really strange memorization game if we were to actually make questions off of it. So 8.5 is also really interesting. It's really cool. Frankly, it's better off in a lab component, in my personal opinion. So there's chapter 8. That was balancing chemical reactions, limiting reactant, and general stoichiometry, dealing with the chemical reaction and calculations with that. Then there's chapter 9. Chapter 9 has a lot of different stuff in it. So we're doing all of chapter 9, all of it. So electrolytes, precipitation reactions, acids, bases, redox reactions, molarity, dilutions, pH, net ionic equations, and gravimetric analysis and titrations. All that's in chapter 9. And we're doing all of it. The bulk of the questions will actually come out of chapter 9. So it just so happens that we by far ask more questions out of this chapter than either of the other 2. If you look at the number of pages in the textbook, or if the number of lecture slides or any of those metrics, you might also notice that chapter 9 usually has the most anyway. So it shouldn't surprise you that more questions will come out of chapter 9 than the other 2 chapters. That's just where more of the content actually is. The last one's chapter 10. So we're only doing the first 3 sections, 10.1, 10.2, and 10.3. This is an introduction to thermodynamics. And if we have time, we will go ahead and touch on this. It's just going to be the very beginning. We'll talk about the rest of chapter 10 for exam 5. So we will continue chapter 10 after exam 4. But we'll do the introduction and ask y'all some questions about that introduction on that first exam. There's actually some calculations that tie actually really well back into chapter 8. So it's part of the reason why we go ahead and do it is because this winds up telling a really nice story about different ways we can talk about chemical reactions and how those all work together. So we took some questions before with the registration. That's what I wanted to say, with the registration. And so one of them was to ask about limiting reactant. Some of them were about things like ionic and net ionic equations. So I went ahead and wrote a problem that does a little bit of everything. And while I know this question has a lot of stuff in it, this question is actually fair game for your exam exactly as written. So I'm going to say that again. I know that this question has a lot of stuff in it. I did that on purpose. This is going to be a long question, and exactly as written, this is actually fair game. So what I'm going to go ahead and do is I'm just going to go ahead and get started in problem solving on this one, because I'm sure the chat is filling up with perhaps interesting questions. But through this question, we'll hopefully address at least some of those. So what this does is this says a flask contains 100 milliliters of a 0.15 molar solution of iron 2 chloride and is added to 200 milliliters of a 0.2 molar solution of sodium phosphate. What, if any, precipitate is formed and how much in grams is produced? Okay, so let's break down what's happening here. So it tells me that I have a flask. So that's a flask. And my flask has iron 2 chloride. So that's telling me I have iron with a +2 charge. Chloride, I could take a look at my periodic table and I could find chlorine as a halogen. So it should have a -1 charge. So therefore I could think about this and say like, okay, so my iron 2 chloride ought to look like that. So I can figure out what that particular compound is. And it also tells me that I have 100 milliliters. And it tells me I have 0.150 molar. You may or may not have seen molarity already. So molarity, to talk about that one briefly, is moles per liter. So this is moles of solute, in which case this is my, I don't really need to put that in parentheses, my iron 2 chloride in 1 liter of solution. That's kind of the reason why we usually just write it as 0.015. This is supposed to be a capital M. When I write it, I tend to do the harsh peaks on the top of my capital M so that I remember that that's supposed to be a capital M. It's not standing for moles or something else because we use M's a lot in chemistry. So I have this information. So it does actually tell me something about how much stuff I have. It's not in grams. It's not exactly in moles. It's in a concentration unit. It's actually in molarity. This then, according to the question, is added to something else. So there's 100 milliliters here, and it's being added to 200 milliliters of a 0.200 molar solution of something different, sodium phosphate. So I'm going to go back to my periodic table. It says I have sodium phosphate. Here's my sodium hanging out as an alkali metal. That's going to be a +1 charge. And phosphate, that's one of your polyatomic ions that we asked you to memorize a while ago. And it's back. So those polyatomic ions are things you're still responsible for. I know they were back in chapter 5, but we are still using them. So this particular compound looks like this, sodium phosphate. So again, I can take those words, figure out what it's talking about, and write a formula based on that. This is also given to me in volume and molarity, not in grams, not in moles, volume and molarity. So, and then the first question actually asks, what if any precipitate is formed? So we're going to go ahead and figure that part out. So I'm going to go ahead and write this up as a chemical reaction. So I've already figured out my 2 reactants. I have my iron 2 chloride. Draw this over here. And I'm adding this to sodium phosphate. And now I need to figure out what my potential products are. We'll look at solubility rules in just a minute. So I'm going to leave myself a little bit of space to put in either those aqueous symbols or those solid symbols. But for right now, I'm just going to figure out what my options are. I already have my different ions. So I'll redraw them over here just so that we've got everything together. So this was iron 2+, this was a chloride ion with a -1 charge, this was a sodium+, this was a phosphate with a 3- charge. So as I go to write my products, what I'm going to do is I'm going to do a double replacement reaction where I'm going to leave essentially my cations in the same places, but I'm going to swap my anions. So before my iron was paired with chloride, now my iron is going to be paired with my phosphate. So in order to do that, see, it's the wrong color. So my phosphate has a -3 charge, so that's going to go down here. My iron has a +2 charge, that's going to be my subscript down there. So again, we need to still use those skills that we had back from chapter 5 with making new compounds. Promised myself I would leave myself some space. I don't know that I'm doing a great job of that, but that's okay. I can move things around if I need to. And then again, my sodium is going to go with my other anion, so that's just going to go with the chloride. That's both a 1-to-1 ratio. So I figured out my products. Now I need to actually figure out what's soluble and what's insoluble. These are going to come from the solubility rules. Also something I would recommend memorizing. The reason why I recommend memorizing these is actually because you need to be able to recognize what type of question you're trying to do. And if you have to look everything up, you're not going to know what's supposed to be happening. So having these handy on the day of the exam, open book, open note exam, is useful. It is. But also having some general idea that all of my alkali metals are always soluble, because here's my little box and it says that I have insoluble exceptions, and there are none. There are no exceptions. So knowing especially the things that have no exceptions can definitely save you some time. So anytime I see sodium, I know it's soluble, always, no matter what. Table says so. So as I go back and I look at my question, every time I see sodium as a compound, I'm going to go ahead and write my aqueous symbol by it, because every time I have sodium, it's aqueous. Then I've got to deal with chloride and phosphate, or my iron, whichever one I can find. So here's my chloride. This says that it only has 3 different exceptions, and iron is not one of them. Okay, so my chloride should be soluble with sodium. That was already going to happen. And then it's also soluble when it's with my iron, because iron was not one of the aqueous exceptions. Leaves me with my iron phosphate. So I still have to find one more. And my phosphate is a negative charge. I don't see it in my top table, so I'm going to look at my bottom table. There's my phosphate. And it only has a couple of soluble exceptions. You might notice that these are the same that were back up there. So the only soluble exceptions were the things that we mentioned were always soluble. So phosphate otherwise should be insoluble. So as I go back and look at what I have, my iron phosphate then should be a solid. So this should be my precipitate. So it gets the solid symbol. So I've answered part of my question already, which was, does a precipitate form? And if so, what is it? So found my precipitate. I did that part. Part 1, done. I have a chemical reaction. What else did the question ask me? I have a chemical reaction. That's probably useful. What if any precipitate is formed? We found out the answer to that. And how much in grams is produced? Well, if I want to figure out how much of a product is produced, and what I was given is I was given amounts of reactants, I'm going to need to use a balanced chemical reaction. So the other part that it's asking me to do is it's then asking me, my goal is to find an amount in grams of a product. And what they gave me is they gave me amounts, liters, well, volume and molarity of both reactants. So it told me about the molarity and the volume of the iron 2 chloride, and it told me the molarity and volume of the sodium phosphate. I have information about both. So anyway, since I've got reactants is what I have, and the goal is a product, I'm going to need a balanced chemical reaction. I wrote this reaction. from scratch. They didn't give this to me. So I need to balance it. So this is also something that was in chapter 8. So 1 iron, 3 irons, that won't work. 3 irons and 3 irons, that's better. Then I've got a phosphate, there's a 2, there's a 2. Then my sodium, I have 6 sodiums, 6 chlorides. Okay, so my chemical reaction is starting to look a little bit messy. We'll just hang in there with it for now. So how are we doing so far? Any questions so far?
Okay, so right now we only have one. The question is, do we need to know what atom economy is?
No, you don't even know what atom economy is. Basically, when we went through for the 4th edition, I really thought, since we were going into this was last summer, and I was actually the one putting together the homework assignments. I really thought, since classes was going to be all the Gen Chem, we'd already been told it was going to be all online, and we were doing all the pre-recorded lectures. I really thought we were going to have extra time in lecture. So I really thought we were going to have extra time for things like green chemistry, which is a personal passion of mine. I was wrong. So no, atom economy is really just in there to introduce you to green chemistry, which is really cool and really interesting, but no, we don't test on that. Okay, so I will just continue plugging along on the math. So one of the other things is that they gave us an amount of both reactants. Anytime you have information about both reactants, this is a limiting reactant problem. So anytime you have numbers and values for both reactants, it is a limiting reactant problem, because you don't actually know which one of your 2 reactants is going to determine how much stuff you can make in the end. You don't know. They didn't tell you. They just gave you some numbers and you get to figure it out. So limiting reactant was one of the questions that I was asked to do in those pre-recorded in the questions that we took beforehand. So my class has heard this spiel before, so I'll give it to those of you who don't know. There are at least 3 different good ways to do limiting reactant that I know of. Since this is an exam review, what I'm going to do is I'm going to use a version of limiting reactant that, 1, is useful for this particular problem, and 2, is usually the most straightforward way if you're struggling with limiting reactant at this point. So I don't know if this is the same way that your instructor did it. I don't know if this is the way that the peer tutoring centers did it, because that's probably dependent also on the person. I don't know if this is the way they did it in your high school. So usually what I do with my class is I show them one way, encourage them to go back and look at other ways, and then give them some time to practice, because I don't know which way you used. And I bet you if you're in a study group, you can find at least 2 different methods amongst your friends. So what I'm going to do, though, is I'm going to use the one where I begin with my reactants and I just solve both of them for product. So what I'm going to do is I'm going to take both of my reactants and I'm going to wind up with 2 different values, both for this iron 3 phosphate in grams, because iron 2 phosphate, my iron 2 phosphate in grams is what I'm looking for. Since I'm looking for the amount of iron 2 phosphate in grams, one of the other things I'm going to need is I'm going to need the molar mass. I know, we're so excited, right? So I'm going to need the molar mass of iron 2 phosphate. I am actually going to cheat, and I'm just going to peek over because I did this problem earlier and I already have it written out. So instead of taking the time to demonstrate where I got all of those numbers, so it's this part of the problem right here. So I did basically just use a periodic table to find 3 irons and 2 phosphates and 8 oxygens. So using all of my coefficients involved to make sure I could figure out how many of each I had. And I wound up with a final answer of 357.49 grams per mole. So I am going to skip over how to do molar masses because I'm going to assume that that's something that we remember. 357.49 grams per mole. I am going to bounce back to that screen just to make sure I wrote down my number correctly. 357.49, 357.49. Okay, good. So that is still a skill that you may need. A lot of times we will provide those numbers for you. So do keep an eye out because oftentimes what we've done is in parentheses next to things, we often have either just like MM for molar mass, or sometimes we've written out molar mass, and we'll often give you these values. So do keep an eye out in the questions on the exam because we may very well have given you the molar masses to help you. If we give you a molar mass for something, you can trust that that is correct. Every once in a while, we have typos and that number is actually wrong, but that's very rare. Also, if we give it to you, you can just trust us. If it's a typo on our end, then tell us and we'll figure it out because you're supposed to be able to trust us. If we just tell you, hey, this is the molar mass of iron 2 phosphate, then you should just take that because we're trying to give that to you to save you some time. Okay, limiting reactant. I want amount of stuff going to product. The stuff they gave me is all in molarity and liters, so I need a way to deal with that. So taking a look at my iron 2 chloride, one of my reactants. They told me I have 100 milliliters of it and 0.15 molar. So 100 milliliters, I'm going to go ahead and get into liters. So there are, so in 1 milliliter, you may have this factor memorized a different way, however you'd like to do it. You want to put 0.1. I'm going to try to hang on to my significant figures. I may fail at some point. This is still of my iron 2 chloride solution. Then whenever you're looking at molarity, it is in this moles per liter. So this is molarity equals moles of my solute divided by liters of solution. This is its definition. But you can also treat this definition as if it was an algebraic expression. So I could go ahead and rewrite and say that my molarity times liters is also equal to moles. I could also rearrange this to say that my liters is equal to my moles divided by my molarity. So even though those units are just a definition, you can actually treat it as if that was an algebraic expression. This is actually the one I'm going to be using because I would like to have moles. That's going to be helpful for this limiting reactant portion of the question. So all I'm then going to do is take my amounts of my iron 2 chloride values. These were out of the question. It was a while ago. 100 milliliters of a 0.15 molar solution of iron 2 chloride. So those are the values I'm using to figure out moles of iron 2 chloride. Times, I already did this in my liters, 0.1123 liters gets me 0.015, what, 3 sig figs, 1, 2, 3 moles iron 2 chloride. Now, since it's a limiting reactant problem, what I'm going to go ahead and do is I'm going to take my moles of my iron 2 chloride, and I want to know for however many moles of my iron 2 chloride, I want to know how many moles of the product that I'm interested in am I going to make. So this is my limiting reactant portion where I'm trying to think through, okay, if I react all of my iron 2 chloride, how much product could I potentially make? In order to get this ratio, I'm going to go back to my balanced chemical reaction, where what I can see is I need 3 moles of iron 2 chloride for every 1 mole of my iron 2 phosphate. So it's a 3-to-1 ratio. So scrolling back to my math, 3 moles of iron 2 chloride for every 1 mole of iron 2 phosphate. Then in my last bracket, what I need to do is, because the question asks about grams, I'm going to go ahead and put this in grams. That's just going to save me some time later on down the road, because that's what I want in the end. So I'm going to go ahead and take that 357.49. And I'll go ahead and just do this math out again. Yes, I did already do this once, but this is also the time where I get a little paranoid, and it's not a bad thing for me to double check my calculations. So I'm going to divide by everything on the bottom, multiply by everything on the top. And what I wind up getting from this, and so my moles of iron 2 chloride will cancel, and my moles of iron 2 phosphate will cancel, and I'm left with grams of my iron 2 phosphate. So I get 1.78745 grams. This is of iron 2 phosphate, because that's what I went ahead and solved for. I just went ahead and solved for product. So this might be the answer, but I don't know. I don't actually know if this is the answer or not. So what I need to do is I need to repeat all of the math I just did for the other reactant. This is part of the reason why no one likes limiting reactant problems, is because you always feel like, but I've just done so many numbers. And that's true. And we're now going to do all of that over again. So now what I'm essentially going to do is start back over and just do the same thing, but now with 200 milliliters of a 0.2 molar solution of sodium phosphate. So same general idea, but for the other reactant. Okie dokie. So this is also helpful, because that way, if anybody's like, I really want to see that again, guess what? It's limiting reactant problem. You are absolutely going to see that a second time. So question says I have 0.2 molar, it's sodium phosphate, and I have 200 milliliters. 200 milliliters. This is the other way I know this factor in 1 liter. So this is 0.2123 liters. I'm going to go ahead and multiply those two together, because I know that molarity times liters is equal to moles. I'll take my 0.200 molar times my 0.2123 liters. Gets me 0.04. Still 3 sig figs, 2 more zeros, moles. Sodium phosphate. So now I have an amount of sodium phosphate. I am going to go ahead and do the same thing, where now I'm using my balanced chemical reaction, because I want to go from moles of sodium phosphate to moles of my product. I want the exact same product, because that's what the question told me I was interested in. So I don't even remember what the other product was right now. We don't care. Problem asked for this thing. Ask for the precipitate, and that's my precipitate. I need my balanced chemical reaction. That's way up here. This is a 2-to-1 ratio. So I've got a 2 as my coefficient for my sodium phosphate to 1 mole of my iron 2 phosphate. So for 2 moles in 1 mole. And then we're going to go ahead and go to grams, because again, that's what the question was interested in. 1 mole of iron 2 phosphate, 357.49 grams. Same game, divide by everything on the bottom, multiply by everything on the top. And we get 7 something. 7.1498 grams of my iron 2 phosphate. So this was my other option. Can actually get both of these on the screen if I will just change and zoom out a little bit. That was the wrong way. There we go. So one of my reactants predicted a 1.78 grams of iron 2 phosphate. The other predicted 7.14 grams of iron 2 phosphate. So the smaller number is the right answer. So essentially, if I reacted all of my, what was this top one, iron 2 chloride If I react all of my iron to chloride, I could make only 1.78 grams. If I could react all of my sodium phosphate, I could make 7.14 grams. So the sodium phosphate's basically overly optimistic. Sodium phosphate's like, yeah, if we just had enough stuff, look how much we could make. But the iron 2 chloride's the one that's like, oh, we don't actually have that much, can't actually make that much, can only make 1.78. So if I cared about limiting reactant, question didn't say I did, but if I cared about limiting reactant, that's actually my limiting reactant, is the one that makes the less amount of product. So I can figure out limiting reactant by taking my amount of reactants, both of them, and moving them both over to an amount of the same product. The math always seems really repetitive. So if you've been doing limiting reactant problems, and you're like, this seems like I'm doing the same thing over and over again, that's actually good, because no matter which version of problem solving you're doing for limiting reactant, you are always going to wind up comparing things that should be the same number or the same chemical compound that you're then comparing. But the question asked me, how much could I make? So the answer to how much could I make is I could make 1.79 grams. 3 sig figs, because that's what we're going to ask for on the exam. So that's the amount of product that I could make. So that's the answer to the first question that was asked. This kind of question, where I actually started with molarities and volumes and I moved to mass of a product, this has a name. This is actually called a gravimetric analysis problem. And this is one of the sections in your textbook. So for people that are like, well, gosh, this just seems like we smushed together molarity and limiting reactant and precipitation reactions, we did. And this is called gravimetric analysis. I often get people to ask, that will ask things like, is gravimetric analysis on the exam? And the answer is yes. But oftentimes they have problems identifying which questions they are, because they just seem like a slightly more complicated version of stuff that we did in chapter 8. And that's exactly what they are, honestly, is gravimetric analysis should feel similar to chapter 8, where we had reactants and we were solving for amounts of products, because that's all it really is. It's got a fancy name because it's more specifically when you're solving for the mass of a precipitate from the concentration and volumes of reactants. So yes, it's a specific type, but honestly, it should feel like something out of chapter 8, aside from this new twist of using molarity and volumes. Questions on this one?
So far, we have no other questions.
All right, that's totally fine. I have some. Okay, so I had a couple things I wanted to make sure that I hit upon. So I'm going to go ahead and make this a little bit bigger so y'all can see it. Pull these up. There we go. So a couple of things that I did touch on, some of these briefly, but I'll make sure that we're more clear. How do I know it's limiting reactant problem? I know because I have numbers. I was given numbers for all reactants. So not just one of them, but I was given numbers for all of my reactants. That's how I know it's limiting reactant problem. I have information on all of my reactants. So that means I have to deal with all of them. The other name for this problem, that was that gravimetric analysis. Then I had a follow-up question because I wanted to make sure we could also tackle this. What if the question asked about the concentration of sodium ions remaining in solution? Because sometimes we'll have a really similar setup, but a gravimetric analysis question asks about the amount of solid left over. That's what we solved for. this question's a little bit different. It asks you for the concentration of sodium ions remaining in solution. So this is going to look a little bit different. We're going to use the same numbers. We're going to use the same setup as we did before, but now we're going to solve for something different. We're going to solve for sodium ions at the end of the reaction. That's what we're going to solve for. So looking back at all of the fun stuff that was going on, this is a good time to consider what's happening to my sodium chloride. So I am actually going to go ahead and redraw my chemical reaction so that this is a bit clearer what's happening. So I'm curious about the sodium concentration at the end. So what's happening is I have my iron 2 chloride, which is aqueous, being added to my sodium phosphate, which is also aqueous. And that's mixing together to give me my iron 2 phosphate, which suddenly we don't care about at all, and my sodium chloride. I will go ahead and put back all of my stoichiometry. This was a 6, that was a 1, that's a 2, that's a 3. If you zoom out just a little bit, nope. No, there we go. So what I now want to know is my sodium at the end of the reaction. To figure out it at the end of the reaction, there's a couple of things that are helpful. So one, I kind of want to know if my sodium's actually hanging out in the reaction itself. Like what is it doing in the reaction? And in order to figure that out, something that can be helpful is to think about ionic and net ionic reactions, because there's some terminology that I'd like to use, but also because one of my other things I wanted to talk about was ionic and net ionic equations. It also was something that people were interested in talking about. So we will be getting back to the math, but first we need to have some language for what to say about that sodium, because there's some really nice assumptions we can make, but I need to make sure you're all with me before I make those assumptions. So what I am going to go ahead and do is this, as I've written it, is what we would term the molecular equation. That's what that is. That's my molecular equation. What I now want is I want my ionic equation. For my ionic equation, what I'm going to do is I'm going to take anything that is a strong electrolyte, and I'm going to break it apart. So if I had any weak acids or weak bases, I would actually keep those all together. I am also going to keep my solid together, but anything that's an ion, I'm going to take apart. I am also going to keep everything balanced as I go through. So we already figured out that my iron 2 chloride is completely aqueous. So I can go ahead and say that I have my 3 iron 2 plus, which is aqueous, and my 6 chloride ions that are aqueous. And then I can also say I have 6 sodium ions that are aqueous, plus 2 phosphate anions that are aqueous. Those are all in my reactants. And in my products, I am going to keep my iron 2 phosphate all together because it's a solid. So this solid right here tells me that it's a precipitate, tells me that the whole thing is going to stay together. That's how I know. I know because of that we already decided that it's insoluble. So we made that decision a while ago, and we're just going to stick with it. Plus, my sodium chloride is all aqueous. I can't fit it all on one line. I never managed to do that. In the times before electronic components, when I was doing this on a piece of paper, I always turned the piece of paper sideways so that I would have this landscape style so that I could actually get this all on there. Usually worked out. Too bad. The whole thing. Okay, there there's my ionic equation. There's the whole thing. So it is much longer, but something to notice is that this is also still balanced. So even though it looks a lot messier because we changed a lot of things, this is still balanced. So just because we changed up the format, we still have a balanced chemical reaction. And all we're doing is anything that's a strong electrolyte is separated. The next one then to do is talk about our net ionic reaction. My net ionic equation. Really what I'm going to do here is I'm going to get rid of anything that's the same on both sides. Get rid of same on both sides. Now, when I say same on both sides, this has to be exactly the same. Not kind of the same, but exactly the same. Exactly, same on both sides. So when I'm looking for things, I know I see these 3 irons, but over on my left, my 3 irons are aqueous. On the right, my 3 irons are solid. That means they're not the same. So when you see that change of going from solid to aqueous, those are not the same, and I can't get rid of them. I have to keep them. So I found something that I'm keeping. That's nice. But I'm going to look and I see my chlorides. So here's 6 chlorides that are aqueous, and here's 6 chlorides that are aqueous. Those are exactly the same. So I can actually get rid of those chlorides when I go to write my new reaction. So things I'm getting rid of my chloride ions. I don't want them. They're the exact same. I can cancel them out. Then I've also got 6 sodiums on the left. I have 6 sodiums on the right. They're aqueous. There are 6 of them. They're ionic. They're all the same. So I'm also going to get rid of those because they are identical. And last but not least, I have phosphate. I have 2 of them and they're aqueous. And when I see phosphate over here, it's a solid. So that's different. So I'm going to keep that. So when I go ahead and write my net ionic reaction, the only thing I'm keeping is I'm keeping things that were different. So I'm going to keep my iron aqueous, and I'm going to keep my phosphate. That was aqueous. And then when I wrote it all together, it became a solid. So typically when you're looking for net ionic reactions, you're usually looking for things where either a precipitate forms, you're looking for, if it's an acid-base reaction, you're looking for water to be formed. You're looking for a weak acid or base. That will also get you a net ionic reaction. Or we also have odd things like insoluble hydroxides. And honestly, the insoluble hydroxide should remind you a bit of the precipitate, except it's going to be on the reactant side. So those are some of the times where you wind up having a net ionic equation. And the reason why I say that is because if everything is soluble, on both sides, so that being my reactants and products, then there is no net ionic reaction, because essentially nothing happened. If everything's aqueous on both sides and everything's soluble on both sides, then nothing happens. You mix some soluble stuff together and it stayed soluble. It just hung out in solution and didn't do anything. So we're basically looking for something interesting to have happened, to actually have a net ionic equation. So got my net ionic equation. Now, part of the reason why I wanted this is because it makes it a little bit easier to talk about what did happen to the sodium. So one of the questions I was curious about is what happens to my sodium at the end of the reaction? My sodium, if you'll notice, was one of the two components that we got rid of. We took it out. Anything that you take out, these guys, they have a name. We call them spectator ions. We call them spectator ions because they don't do anything. So usually if you are something like a spectator at a sporting event, these are people that go to sporting events and they watch. They're in the stands. So they're there. They may be cheering on the actual reaction that's happening, but they don't do anything. They don't participate in the reaction itself. They are not doing the actual chemistry. They do not get to play ball. All they get to do is sit back and watch. So these are spectator ions. So sodium is a spectator ion in this particular chemical reaction. The reason why I wanted to know that is because whenever it says something like, how much is there at the end of the reaction, this is one where I don't actually have to worry about how much reacted, because none of it reacted. All of the sodium is just in solution. It didn't go anywhere. It didn't do anything. So it's really tempting to try to do some sort of like limiting reactant stuff. But that sodium was aqueous when we started, and it's aqueous in the ending. So there is some math we need to do in order to figure out how much of it we have. So we are still going to do math with it, but none of it reacted. None of it's gone. So the amount I have in the beginning is still going to be the amount I have in the end. Notice I say amount. This is going to be my molarity is going to be the same. I'll show you what I mean. Okay, so what I'm going to do is I'm going to copy this information, because now what I'm curious about is I'm curious about my sodium. So this question tells me, I'm going to change my view again, zoom back in. So same exact chemical reaction, talking about it for almost an hour now. But I started off with sodium phosphate. And we've decided that all of the sodium I have, all the moles of sodium that I have in the beginning, are the moles I have in the end. There's something very specific that happens, though, which is I had stuff in a flask. That's not very flask-like. That's sure, that'll be a flask. I had stuff in a flask and stuff in a beaker. So originally I had 200 milliliters of one thing and 100 milliliters of the other, and I put them together, and in the end, I should actually have 300 milliliters. So something really specific is happening here, which is my sodium's not reacting, but it is getting diluted. Because there's more volume at the end. So I'm not caring about this stuff anymore. Now what I care about is my final concentration of sodium. That's what I'm trying to solve for. Okay. So what I'm going to do is I'm going to figure out my concentration of sodium in the beginning. So we've already talked about the fact that what molarity is. One of the other things we need to mention is the fact that since I have this sodium phosphate, when I break this apart into ions, I would actually have 3 sodium ions and 1 phosphate anion, which means when I talk about my sodium phosphate having a molarity, my molarity of my sodium phosphate is 0.200 molar for my sodium phosphate. When I talk about my sodium ions by themselves, now essentially I have 3 times as many. So the amount of the molarity of my sodium ions when I begin should be 3 times as much. So my sodium concentration in the beginning, my initial, is actually going to be 0.6 molar. I can show that mathematically. So for those of you that are like, whoa, now, what just happened here? So essentially what I'm saying is I started off with 2.00 molar, or moles of sodium phosphate in 1 liter. And then what I'm saying is that for every 1 mole of sodium phosphate, I actually had 3 moles of sodium ions. My moles of sodium phosphate cancel. I'm left with then moles of sodium ions per liter. So I actually am still back in molarity. Moles of sodium per 1 liter. So I can do that mathematically, or you can reason your way through it and say, aha, I have 3 times as many, I multiply by 3. So initially I have 0.6 molar sodium ions, and from the problem I have 200 milliliters. So that's my initial setup of my initial volume. Then what I figured out is I figured out that I have 100 milliliters that I'm adding to 200 milliliters, so I wind up with 300 milliliters. So my final volume is 300 milliliters. And the question actually asks, what is my final molarity? This is a dilution problem. There's actually an equation for this, where what I can do is that's M1 V1 equals M2 V2. So I can actually go ahead and use this equation. So I started off with 0.600 molar and 200 milliliters. And I'm going to an unknown molarity, that's why I'm doing this problem, and 300 milliliters. And then all I have to do is solve for that second molarity. 0.6 times 200 divided by 300. My new molarity is 0.43 sig figs molar. And these are still sodium ions. If you didn't catch that this was a dilution problem, if you didn't catch that dilution was what was happening, and so therefore you didn't use that equation, you can still solve this problem. So if you didn't catch that it was a dilution, essentially you're going to wind up doing the same math, but you're just going to reason through it slightly differently. So if you didn't catch the dilution, what you would have known is you would have known still this information that we have 0.6 molar and 200 milliliters. So this is still information that we would have known. So if you didn't catch that it was a dilution problem, you still would have known this 0.6 molar and my 200 milliliters. And then that the final volume is 300 milliliters. So we still have this information. There's one more way to solve this problem, which is to go ahead and do what we did when we first started, which is to go ahead and say, I can take my molarity times my volume in liters to get moles. So I can take my 0.6 molar times 0.2 liters, get 0. Yes, I am going to use a calculator for this relatively straightforward calculation because I don't want to mess up my decimal places. Moles. So these are the moles I have of sodium. We said that they weren't reacting. Nothing was happening to my sodium ions. So all I have to really worry about is that I have sodium ions in a new volume, which happens to be that 300 milliliters. So I can go ahead and solve moles per liter because I know what the units of molarity are. 3 sig figs, because that's what we're going to do on the exam. And hey, we got the same answer. So this is one of those cases where I did want to show off the dilution equation, but depending on how the question's worded, a lot of times if you recognize, hey, nothing happened to the moles, then you can solve this problem without the equation. You wind up doing exactly the same math. So technically you're still really using it. You're just going through it stepwise. But if that equation is either intimidating or you're like, what if I reason through it a different way? Guess what? The best thing about chemistry is problem solving usually has multiple routes and many of them are valid. So as long as you're making the right assumptions that things like your sodium never reacted with anything else, you're good to go. Questions so far?
Let's see, we have a few. We have, how come you do not find the molar mass of sodium phosphate and iron 2 chloride when finding a limiting reactant?
Okay, so scrolling, back to the beginning. So essentially, so the question is, why didn't I bother with doing molar masses of my reactants? I didn't bother because what I had was I had volume and molarity. So with volume and molarity, the goal of limiting reactant, always the goal of limiting reactant is going to be to compare reactants and products. When my goal is to compare reactants and products, I compare in moles, always. So no matter what, when I'm doing a limiting reactant problem, my comparison has to be in moles. That's what all of my stoichiometric coefficients are in. They could also be in molecules or formula units, but those are really small. So I'd rather work in big numbers. So these are technically all in moles, and I have to use my balanced chemical equation. So the goal of a limiting reactant problem is actually to get to moles. That's the goal. So in this particular case, since I wasn't given grams to begin with, I'd never needed my molar masses. The only time I needed a molar mass is when it gives me grams or when it asks for grams. And the only time that happened was the precipitate. So you didn't see any molar masses for the reactants because my reactants were all in molarity and volume. If my reactants had been in grams, then I would have needed molar masses. So if I had grams to start with for my reactants, I absolutely would have needed molar masses because the goal is always moles. I'm going to write that down over here. Limiting reactant, the goal is moles. So however you get there, so if you were given grams, you would need a molar mass. If you're given moles, you're already there. And when you're in molarity and volume, then we had to do some different math to get there. But the goal was to compare in moles when we use the balanced coefficients. What's next?
Where does a solid precipitate stand on the electrolyte scale? Is it considered a non-electrolyte or a weak electrolyte?
We're going to consider something that's insoluble to be a non-electrolyte. And what we often do is we often just ignore them on the electrolyte scale because oftentimes the faculty argue about where that scale, where that stands. So a lot of times we actually just ignore them. So honestly, when you're looking for weak electrolytes, if new space, different space down here. So typically if you're looking for a weak electrolyte, while yes, part of our definition is a slightly soluble ionic compound, we didn't give you anything to figure out what that was. Slightly insoluble compound is part of our definition of a weak electrolyte, you have no ability to figure out what that is. None. Because the table in your book just does soluble or insoluble and doesn't give you a range on that. The things that you can identify is you can identify weak acids and you can identify weak bases. So those are things you can identify. So when you're looking for a weak electrolyte, you're really keeping an eye out for a weak acid or a weak base, because you actually don't, unless we describe it to you with these words, a slightly insoluble compound, you don't have a way to figure that out on your own. So you either have to be told, or you're actually looking for a weak acid or a weak base. It's a good question, though, by the way. It's a good question, because there are slightly soluble, slightly insoluble compounds in the real world, but chapter 9 doesn't actually give you the skills to work with them. Chapter 17. Sorry, the fourth edition of the textbook rearranged the chapters that are in Gen Chem 2. So I used to have them memorized, and I do not right now because they moved around a little bit. But yeah, so we'll come back to precipitation reactions in Gen Chem 2, and then we'll have ways to deal with that. But good question. Other questions?
All right, so we got two more. First one is it necessary to convert milliliters to liters or vice versa before using the equation?
So it depends on what the goal is. So the question is, do you have to convert? So I don't know if you caught the fact that in my dilution question, I actually didn't convert here. And that's because what I was going to do is I was canceling out my volume units. So here in my dilution equation, as long as they're identical, I didn't have to do any converting. They did need to be the same. So I did need them to be the same volume unit. So as long as they're the same, this works out for me just fine. If they were different, I would have had a problem. But since they were the same unit, I could actually leave it just like this. I believe your textbook and Alex goes ahead and walks through things in millimoles. So instead of converting from milliliters to liters, they just go ahead and multiply them together and do everything in millimoles, which works just fine, by the way. If you are a fan of millimoles, you are welcome to do that, and you are welcome to keep it like that. It is my personal habit to go ahead and go from milliliters to liters and just work everything in moles instead. Honestly, that's just my personal habit because I thought it would make more sense, because we've been doing moles for so long that it was easier to do the conversion between milliliters to liters than it was to talk about what exactly a millimole was. But again, that's my personal preference. There are really good reasons why you could work in millimoles instead of moles. It's just my personal preference that anytime that I was actually solving for moles, I went ahead and converted. So, but there are definitely problem solving ways where you don't have to do that. And Alex definitely does it. I thought your textbook did too. And I believe Dr. Wong, who did the pre-recorded lecture videos for chapters 8 and 9, I think he actually likes millimoles. So I think he actually does his work in millimoles. So if you wanted to see millimoles and you wanted to see that, you could actually check out those Microsoft Streams videos and the pre-recorded lecture materials, because I believe he actually does his work in millimoles. Other questions?
All right, last one. Can you please go over the different types of acid and base reactions?
Oh, sure. Can I do all of them off the top of my head, or do? Okay, because the ones I think. So here's the ones I think we've got. I think I have strong acid, strong base, and I'll do an example of each. I'll at least put up an example of each one of these. Then strong acid, weak base, weak acid, strong base, because I'm doing all of these in this order, someone's going to wonder where it is, so I'll write it down. Weak acids, weak base, but I'm not going to do this as an actual example because this is a 13-12 topic. And then there's a funky one, which is insoluble hydroxide with a strong acid. Let me double check in the notes to see if I missed anything. So yes, I am scrolling desperately through my book. So there's the insoluble hydroxides that I didn't want to miss. Okay, good. That's strong acid, weak base. Okay, good. Okay, got it. Well, basically, I knew there was the acids with insoluble hydroxides, and I wanted to double check to see if there was anything else I was missing aside from that. Okay. So I count 4. So I am just going to give some relatively classic examples of these. So the strong acid that we usually use the most is hydrochloric acid. The strong base we usually use the most is sodium hydroxide. That is because both of these are cheap when these go together. This is actually also a double replacement reaction. So here's my sodium and here's my chloride. And here's my H and my OH. So technically I could actually write this as HOH like this. Nobody does that. Everybody actually writes it as water. But technically that is what's happening. This is actually a double replacement reaction. And my HCl. If I wanted to talk about this as being a net ionic equation, I am going to cheat. I'm going to show you how I cheat. So I often, when I'm doing net ionic equations, when I tell you to do a net ionic equation, I will always encourage you, when you're practicing, to go from the molecular, that's what this is, to the ionic, to the net ionic. The reason for that is because on exams, we could ask you for any of those 3. We could ask you for molecular, we could ask you for ionic, we could ask you for net ionic. So as you're practicing, it's worthwhile to go ahead and say, where is everything going and what all is happening and which ones are my spectator ions? Because we like to ask all of those questions. But just in case you're curious, if the goal is a net ionic equation and that's the only thing I wanted, how I usually do this is I look for the thing that's different. So in this case, I have aqueous. I'm looking at my state symbols. I'm looking at aqueous, aqueous, liquid, aqueous. There's my liquid. I'm going to have that because that's the thing that's different. Whatever that different thing is, that is definitely what I'm going to have. Then I need the things that make that a liquid. And now this works because of my strong acid, strong base. So there's my net ionic equation for strong acid, strong base. People usually get a little weirded out because they think there should be more stuff in it, but there's not, because these two are both strong electrolytes. Strong electrolytes, you write out the whole thing. And my sodium chlorides, you're going to see sodium and chloride as spectator ions a lot. So there's that guy. Strong acid, weak base. I'm going to keep my hydrochloric acid. I'm going to draw the typical weak base, which is ammonia. This is not actually going to make water, which is a little bit strange. This is going to make sodium chloride, or ammonia chloride, pardon me. Ammonium, one more time, ammonium chloride. When I start to think about what's going on here, that's when I kind of need my ionic just to think this one through, because this is a little bit strange. My hydrochloric acid gets all written out, all the pieces, all the parts. Everything's aqueous. I am going to ignore my state symbols. And then ammonium is another polyatomic ion. So then when I go for my net ionic reaction, everything's aqueous. There's no water created. But I've got something that is the same on both sides. It's the chloride ion. So that's the thing I get to get rid of. So when I write my net ionic reaction, it actually looks like this. I'll put the aqueous symbols back in. So my weak base looks a little bit strange, but there's no way that weak base doesn't dissociate, it doesn't ionize. So that's what the weak base looks like. It stays all together, it's a covalent compound. And since it accepts a proton, it looks fairly drastically different on the other side of the reaction. Okay, two more. Weak acid, strong base. Again, I'm just going to do the ones that are kind of classic. C2H3O2, that's acetic acid. With a strong base, that's sodium hydroxide. Makes sodium acetate. That is a double replacement reaction. Acetate is on your polyatomic ions list. I know saying polyatomic ions list is the least favorite thing of yours that comes out of my mouth. That's too bad. This is also a good time to take a look at that ionic equation, because my weak acid has to stay all together. It's really tempting to draw this as falling apart, but it doesn't. My weak acid, for the most part, is all together. When I say for the most part, when we talk about weak species and the fact that they do not ionize 100%, it always sounds like, I don't always eat vegetables, but I eat vegetables. It happens. This is more like, what's something that happens super rare? Drawing a bit of a blank. Weak acids and weak bases only ionize like 1 in 1,000, 1 in 10,000, 1 in a million. So this whole like weak acid ionization thing, it's kind of more like winning the lottery than it is like eating your vegetables. So your weak acid ionization, we're just going to roll with that. I know the numbers are a little bit bigger than I meant them to be, regardless. Weak acids ionizing a lot more like winning the lottery. Does not happen very often to very many people. So your weak acid ionization is so incredibly rare. We don't talk about that as being a thing. So it does actually stay all together because this is the weak species. Because really, honestly, because it's a weak electrolyte is why we do that, which is also, it's also a weak acid. We could say that too. But that does stay all together. It did not win the lottery. Don't talk about it like it won the lottery. You know the odds of that are incredibly rare. Don't talk about that like that's your goal, your life plan. Won't work. So sodium's the same on both sides, so that's the only thing I'm allowed to get rid of. My net ionic reaction is kind of long because we are not going to assume that my weak acid won the lottery. We are going to assume that my weak acid does its job and is a contributing member of society and did not win the lottery, is not randomly independently wealthy because of a random set of numbers. It's a weak acid. It is in the 99%. Still made water, still sticks around. One more. It doesn't come up very often, but it's worth mentioning because it's a thing. Insoluble hydroxides. So in your strong bases, there's a couple of your alkali metals that are not strong bases. This is one of them. Essentially, it is a rock. It is. It's a rock. It's solid. It's insoluble. It's a rock. It doesn't do anything. Kind of boring, honestly. Until you pour hydrochloric acid on it, and then it does something pretty cool. It dissolves. So acids will occasionally dissolve rocks. That's a thing that they do. Magnesium chloride, aqueous. plus water. So again, I'll go ahead and do the ionic reaction. I was only lazy the first time. It's a rock. It stays all together. My hydrochloric acid, however, gets to be separated. Those are both aqueous. Aqueous. Magnesium chloride is aqueous. I know I didn't flip over how I knew that because I have too many things memorized. Actually, I don't. You need to have this memorized. I don't have too many things memorized. There's my chloride ion. Magnesium is not one of its insoluble exceptions. So magnesium chloride is soluble by your solubility guidelines. Also, in case you're curious, magnesium hydroxide is insoluble by your solubility guidelines. So that is actually all consistent. Where was I? Magnesium, aqueous plus chloride 2, chloride, aqueous plus water. Are we excited yet? Okay, that's ionic, my net ionic. That's a solid, it stays all together. And then what do I get rid of? Oh, I didn't balance this. Whoops. 2, 2, 2. There we go. Oh, 2. That's better. That's much better. Apologies for the slightly high-pitched whoop sound. That is the sound that actually usually makes my dog come running if I'm in the kitchen, because that like, whoops, I made a mistake. High-pitched noise is also the sound I make when I drop something. And my dog knows what that means, because when I'm cooking in the kitchen and I make that noise, that means I have just dropped food on the floor. If you've never had a pet before, pets will often show you your random personal habits in ways you did not know existed. Because I've accidentally trained my dog to come only when I'm in the kitchen to, yep. Okay. Oh, so yeah, those are your acid-base reactions. There are a lot of them. But realize that all the time, except for the weak base reaction, these all made water. So they usually make water. My weak base is really the only exception to that. And that's, everything's aqueous. So there's water, it's around. But this is, do you see water in the products as you're keeping all your chemical reactions balanced with everything else? I also know I did those all pretty quickly. This is one of the disadvantages of everything being online is I can't see y'all. But this is actually also part of why I tried to grab reactions that should have already been in your notes, because these are the classic ones. So I didn't make up new ones. So for those people frantically scribbling, these should be the same ones that y'all covered in lecture. I have not gotten to talk about insoluble hydroxides with my 8 a.m. class, but I do with my 9 a.m. class. So it also depends on where you're at. But I'm weird, I covered molarity early. Other questions so far?
Nope, that's all of them right now.
Okay, great. So so pardon for the scrolling, but these were some of the other things that came out of the asking questions in advance. So this is my other set. So I'm going to just take that and scroll back down to give myself some space. I'm going to make that bigger so I can actually read it, and so can you. So two definitions, differences between them in acids and bases. So there are two different definitions. One is the Arrhenius definition. Oh, brother, I always forget where the H goes. And I really should spell it correctly. It would be nice if I did that. But I gotta go back to where I did acids and bases. So for those of y'all that are not in my sections, I do actually rearrange chapter 9 kind of a lot. I don't know why electrolytes and I don't get along. I don't really know why. Honestly, because part of what I had a problem with is it kept wanting us to talk about weak electrolytes without having to find a weak base and a weak acid, and that just always really bothered me. So I moved them so that I could go ahead and talk about acids and bases well, and then do electrolytes. So I copied the slide in so I could get the spelling of Arrhenius correct. It is 2 R's. Okie dokie. So this is what I wanted. So here's our acid-base reactions, and there are 2 different definitions. One is the Arrhenius definition. An acid releases H+ in solution, usually will react with water to produce hydronium ion. So a lot of times when you see this, HCl fits beautifully. Honestly, so do most of the acids that we think about. Our weak acid also fits this just fine. Our acetic acid fits it just fine because there's this H in front and it's going to go away. So that H+ is going to be released into the water. In an Arrhenius definition, my base is supposed to release hydroxide in solution. This works fine when you're looking at something like any of your strong bases. So your strong bases work great because your strong bases are all hydroxides, and they will go ahead and release the hydroxide that they have in water. They're ionic compounds, they will dissociate, release hydroxide in water. No problem. The hard thing then is identifying this one as a base, because it is, but it doesn't have any hydroxide to release. There's no hydroxide to release, so it can't do it. Ammonia would not be a base according to the Arrhenius definition. It doesn't have any hydroxide, so it can't release hydroxide in water. It doesn't have any. It can't do it. So your Arrhenius definition works pretty well for acids, and for pretty much all the acids we're going to talk about for all of the acids. Period. For all the acids we're going to talk about in 1311. In 1312, there is actually a third definition of acids and bases. I know you're excited. That's really what you wanted. It's in Gen Chem 2. We won't talk about it now. In case you've seen it before or heard of it before, the other one is Lewis acids and bases. That's in Gen Chem 2. Bronsted is going to let us look at ammonia as a base. So ammonia then, as long as it can accept a proton, I have a base. So then what I'm going to be looking at is if I have water, I'm going to draw my double arrows since it's a weak species. What I can look at is I can actually look and say, okay, here was my thing, here was my compound. What happened to it? When I look and I see what happened to it, in between these two, it gained a proton. It gained an H+. I can tell that because I can see how many hydrogens it has. It had 3, now it has 4. Also, it was neutral, now it's positive. So I can see that in a couple different ways. So since it gained a proton and now it's positive, we call that a proton acceptor. And since it's a proton acceptor, that makes it a base. Anytime we have an acid, or anytime we have a base, we're going to have an acid. That proton had to come from somewhere. So then I have my water that had 2 hydrogens. Now it only has 1 hydrogen. Also, it used to be neutral. Now it's negative. So my water lost a proton, changed charge. So that means it donated a proton, and therefore it's an acid. So the differences in the definitions, as far as you're concerned, the acid actually looks super similar. So as far as our acids are concerned, between these two definitions, my acid definitions are actually ridiculously similar to each other. One of them says it releases H+ in solution. The other one says it donates a proton. Really, the only difference is that for a Bronsted, we're really looking for that proton to go somewhere. An Arrhenius is just like it releases them, like releasing doves or releasing balloons. They just release and they're gone. Bronsted is saying that it went somewhere. It went from one thing to another thing. Hey, where did that go? So the Bronsted definition's a more sophisticated, a more responsible definition of acids and bases, because you're not just releasing things out. You're saying, hey, where is that thing? Where'd it go? Talk to me about where my stuff actually went. So those are some differences in between the two sets. So thinking about acids and bases and thinking about the differences in between the definitions. In general, something else to note, once it's an acid, it's always an acid. Once it's a base, it's always a base. So it doesn't matter how you can identify it. If it's an acid, it's an acid. If it's a base, it's a base. There's no way to make things be an acid in one system and a base in another. It doesn't work. It does not work. Okay, so that was definitions. Weak versus strong. You memorize the strong list. And then if it's not on the strong list, it's weak. That's it. I will go ahead and grab those. But I think sometimes people are looking for something interesting and impressive, and it's not. It is just, there's some stuff to memorize. And yes, I am going to add those couple of extra compounds on there just to be on the safe side. So here's my strong acids, my strong bases. I'm going to go ahead and say that there are actually 10 strong acids, H2SeO4, and then the bromine versions of the chlorine versions, HBrO3, HBrO4. So you basically memorize your strong acids and bases. That's how you know that it's a strong acid or a strong base, is you have these lists memorized. Those are the strong ones. Weak acids. There are two different ways to identify something as being an acid. One is having hydrogen in front. So you may have noticed that when I drew acetic acid, I drew it like this. And I have one proton, one hydrogen here. I have 3 there. This one up here in the front is an acidic proton. These over here are non-acidic protons. You've seen hydrogen be in covalent compounds before. It can't always come off to go into solution. It can't always ionize. So sometimes it can, sometimes it can't. For you, what we're going to do is we're usually going to put that proton in front. The one time when we don't always do that is sometimes we will write things out as a structural formula. So still using my acetic acid actually as an example, it looks like this. CH3COOH. This thing in the back is a carboxylic acid. And it has one ionizable or acidic proton. We could also just tell you, by the way, we could also just say a weak monoprotic acid. So we could also just use language and tell you, hey, it's weak. So we can also do that. When you're looking for weak bases, really what you're looking for is you're oftentimes looking for ammonia, or you're looking for things that look like ammonia. So ammonia is a weak base because of the lone pair on it, because it can accept a proton. So you can also identify these by their definitions. So there's my lone pair. Here's my proton. That ammonia is going to form a coordinate covalent bond with that proton, and it's going to accept it. So as long as it has this lone pair, usually what I tell people to do is look for nitrogens. And basically, if it has a lone pair, then it's a base. But realize the other thing you should be able to do is you should also be able to use the Bronsted definition or the Bronsted-Lowry definition. Some people call it the Bronsted definition, some call it the Bronsted-Lowry definition. I'm the person that likes the fewest number of syllables. Basically, if you have products, you should be able to identify the base because it accepted a proton. In products, did it accept a proton? So you should be familiar enough with the definitions to be able to identify them in a chemical reaction. It's 5:30. It's time for me to pause and ask for questions again. So questions so far?
We just have one. Can a compound ever be both a Bronsted acid and a Bronsted base?
So a compound can be a Bronsted acid. So a compound can be one or the other, just not at the same time. I'll show you what I mean. So can a compound be an acid or a base? Yes. I'll show you an example in just a minute. But can a compound, I'm going to be really specific, in Chem 1311 be an acid and a base at the same time? That is like an Arrhenius 2Rs. An Arrhenius acid, but a Bronsted base. This one is no. And yes, I am super specific in saying in Chem 1311 because in upper level classes, you get bigger molecules. Bigger molecules can do both. But this is 1311. We're just trying to get y'all to identify what's going on. So the poster child for yes is water. So we actually, no, hold on. Okay, good. So we already drew water to look like this, where water was the acid and it donated a proton. But I could also actually have water acting as a base, and I could go ahead and have water working with hydrochloric acid. Make my life easier. And then this becomes H3O plus Cl minus. So I can have water acting as both and as either an acid or a base. So same compound could be an acid or a base, yes. But acting as an acid and a base at the same time, like being an Arrhenius acid but a Bronsted base, no. Other questions so far?
Can you explain why NaC2H3O2 can be considered a strong electrolyte?
Oh, sure. So as I look at this compound, I want to identify it as a strong electrolyte or a weak electrolyte. I want to identify the type of electrolyte. So that's my goal. So the question is, why is it a strong electrolyte? So the question already told me that it was one. What's going on? As I look at this compound, what I want to think through is that is a metal. There's my periodic table. There's my sodium. It's green. It's a metal. This stuff here is a polyatomic ion. Emphasis on ion. So this is really talking about how does my sodium plus and my acetate ion go together. So this actually is going to ask about solubility rules. So that's actually what this is going to be based on, because the compound alone just says, hey, here's a sodium and here's a polyatomic ion. Is that going to be soluble or not? So then what I'm curious about then are my solubility rules. Again, you should have these memorized. It would help you a lot. But if you don't, because it's Sunday and you've got 6 days, there is my acetate. So there's that C2H3O2. And it has no insoluble exceptions. None. Plus, there was also the sodium. I should have shown that too. I also have sodium, which also has no exceptions. So both of those ions lead this to be soluble. So since this is soluble on both counts, this should be a strong electrolyte. I know there are some of y'all out there that when we were doing the acids and bases portion, kept waiting to hear a certain word. And there's a certain word that we actually don't use until 1312. So I'm going to go ahead and write it down, but I'm also going to write it down 1312 only, which is conjugate. Acid or conjugate base. So I know that that was a term that some folks were waiting for. You unfortunately have to wait until late February, early March. Late February, depending on when the semester starts. But that's in chapter, nope, don't remember what chapter it's in because they moved. Anyway, conjugate acids and bases are in 1312. So for those people that are like, but that is totally a conjugate base, and I could totally do some acid-base chemistry with that acetate ion, you're absolutely right, you can in 1312. Unless you have a chemical reaction that tells you something about it, accepting a proton. So if I have a chemical reaction that tells me this accepts a proton, then I would know that this was a base. So it can. That would be super useful. C2H3O2 minus looks like this guy, HC2H3O2. And in fact, it can, so this can accept a proton. So this actually is a base. But when it's paired with the sodium, we just care that it's soluble. So I understand where that question comes from. And it's nice, it comes from having more information. But as we look at sodium acetate, we're just gonna identify it as being soluble and therefore a strong electrolyte. We don't care about the fact that it's also, that acetate ion is actually also a base in that particular context. But it is also a base, weak base. Other questions so far?
That is the last one I have on here.
Okay, cool. I'm gonna hop over here and hop back again. So I hope that this, no, it's still moved. Okay, hold on. I have to close OneNote and reopen it because occasionally my, there we go. occasionally my screen just does that, where it just hangs on to something I wrote and doesn't actually put it in one note and just makes it hang around in the open air. Not really what I was going for. Okay, I know I had some more questions. Oh, okay. Oh, why does water have a neutral pH? This came from the questions taken ahead of time. Why does water have a neutral pH? So there are two different answers to this question. There is the bad answer that I will give first, which is because it does, which is a bad answer. The better answer about why it has a neutral pH is because of something we haven't actually defined. So we have talked about this notion of pH and either proton concentration or hydronium concentration. These are, for all intents and purposes, the same thing. Essentially, when you talk about water, water actually does ionize all by itself. And when it does so into two components, either into a proton and a hydroxide, or if you prefer to think about it like this, into a hydronium ion and water. These are exactly the same, just depends on how many waters you want to think through. Whenever we actually want to, so when we talk about pH, we are talking about these guys. Whenever we're talking about pH, we're looking at one of these species, and that's what we're identifying, and we're saying this is how much we have, this is what's going on in water. pH is on your exam, by the way. So for those of you that are thinking I'm talking about pH for no good reason, pH is absolutely on your exam. It's the log of that thing we were just looking at. Or you can do it backwards and do 10 to the negative pH. Will give you the either hydrogen concentration or hydronium concentration. These are actually the same thing, which I know proton, hydronium, hydrogen ion all being the same thing is not your favorite thing ever, but that is true. As far as why water is neutral, we actually define neutral as being when my proton concentration is equal to my hydroxide concentration. So this is the definition of neutrality, is when the water ionization, the two pieces it breaks into, you have the same amount. This is when water is neutral. Now, and this gets us slightly, so this part's okay. It's still a little bit more in depth than what we usually do for Gen Chem 1. This is the part then that's kind of step beyond, which actually is in Gen Chem 2. At 25 degrees Celsius, this happens to be a certain number, which is 1 times 10 to the negative 7th molar. Which means, using your pH equation, we're back in Gen Chem 2, Gen Chem 1, pardon me, back in Gen Chem 1 now, times to the negative 7th molar. This means that my pH is 7 at 25 degrees Celsius. This does actually mean that your neutral pH is not the same if you're at a different temperature. Your pH changes depending on what temperature you're at. That is a Gen Chem 2 topic. So you might see us tell you that particular reactions are happening at 25 degrees Celsius. That's an artifact from the fact that your instructors like to be correct and like to be accurate. So oftentimes you might see us go ahead and give you a temperature and say, hey, this is happening at 25 degrees Celsius. If you see us do that, that's just because there's a little bit of insider information happening, which is that your pH actually changes depending on your temperature. Again, how that actually works is a Gen Chem 2 topic, so I won't go into it, but one of the pre-submitted questions was about why is neutral pH 7? That's because of the definition of what neutral is. So your pH is not actually 7 if the temperature changes. around off of room temperature. Doesn't change a whole lot depending on how much it does, but anyway. And then there was one last question that I already had pre-done, which I think was just the most common question people get wrong. So I've got bad answers for this. So the first thing that people get wrong is whatever they like the least. This is part of the problem with things like, well, how many of this kind of question are there? Is because whatever you like the least is what you're going to be like, oh no, they did ask me that. Chapter 9 has a lot of stuff, y'all. A lot of stuff. The other thing people usually get wrong is the stuff that's not in ALEX. So this is where we have those end of chapter questions. And there's one thing in particular that I've got that is not in ALEX. We do cover it though. We do cover this. But this is the thing they usually hear from students after the exam, that they had no idea what that was. They'd never seen it before. We'll ignore the fact that I definitely covered that in class, but that's okay. But the most common question people actually get wrong is something that's an oxidation or reduction section that's not in ALEX. And it's not because ALEX just doesn't have questions on it. We would give it to you if they did, but they don't have one that's at the correct level. So what is that question? What's it look like? It's this question. So there is a table that we will give you on your exam, and it's called the activity series. And it's going to have lithium at the top of the chart. This is how you'll know it's the activity series. It'll have lithium at the top of the chart. What these are is these are going to talk about what is most easily oxidized, what is most easily reduced. Now, I understand that for a lot of the sections, mine included, we haven't actually defined oxidation and reduction yet. That's what I'm doing on Monday. So I'm going to go ahead and walk through an example, not the one that's here on the slide, but I'm basically going to try to show you what this chart does without defining oxidation and reduction, which might be a mistake, but I've about 15 minutes left. So let's see if I can do this. So there are some things that we think you know. Thinking about lithium, going back to a periodic table for a minute and thinking about lithium. Lithium, in all of its wildest dreams and goals, lithium, it's an alkali metal. It is so close to being like helium. This thing's ionization energy is really low. Guys, it doesn't want that extra electron at all. It hates the extra electron. It wants to ditch the extra electron. It doesn't want it. There's a reason why we're so comfortable with our alkali metals being positive. They like to be positive. They don't want the electron. They haven't wanted the electron this entire time. So when we look at this reaction of lithium getting rid of an electron, this lithium, where lithium is positive, this is a very happy lithium. This would get the biggest smiley face emoji. I should have grabbed more emojis. Lithium plus, super happy. Lithium solid, unhappy. It does not want that extra electron. It doesn't want it. So when we're on this chart, things closer to the top of the chart want to be positive. Things closer to the bottom, and we haven't gotten to talk a whole lot about gold. So I understand you're like, I don't know about this thing's personality. Closer to the bottom of the chart, being solid makes them happy. So things at the top of the chart really want to be like the products that are positive. Things that are towards the bottom of the chart want to be like the reactants that are shown here. So what's going to happen is we give you a set and we say, hey, here's lithium solid and here's 10 2+. Does this make any products? And really what you're looking for is you want to figure out if these are happy like they already are in comparison to each other. Now I did cheat. Lithium's at the top of the chart. So we already know that lithium is at the very top of the chart. Lithium is super whiny and unhappy when it's a solid. It is. Tin, on the other hand, has got to be lower than lithium. So it's kind of in the middle-ish, but 10 could go either way. It's fine. So I don't remember, but it's fine. Either way. Lithium, though, is super unhappy. 10 is lower on the chart, this 2+. So 10 will actually take the electrons from lithium. So lithium will actually become happy and will actually become positive. 10 will go ahead and take those electrons from it and become solid. And I know that all because of where they are on the chart. So this is all about where things are on the chart relative to each other. Does anything happen? So trying to take a look at one more example. Again, going a little bit closer to where things are. We're going to do tin as a solid and chromium 3+. I'm ignoring balancing, by the way. There are other topics that are also in oxidation reduction that I am blatantly ignoring. They are also on your exam, but I can't cover all of oxidation reduction in 10 minutes. I'm not that good. So this one has zinc, but this is the question people miss the most often. So this one has zinc, and it gives me this one, and it gives me chromium over here. Top of the chart, the zinc is closer to the top. If it's closer to the top, it is unhappy as a solid. It doesn't want to be this. Chromium is on the bottom. It is also unhappy, like it is, because of where they are in the chart in comparison to each other. So these actually will swap places. I know what they become because of the chart. So this becomes zinc 2+ and chromium solid. If I had the opposite pair, if I had zinc 2+ and I had chromium solid to begin with, then what happens is, then what I see is I have zinc plus compared to chromium solid. Zinc plus closer to the top of the chart. This is happy. That's awesome. Chromium solid lower on the chart. That is also super happy. If this is the case, you have what we call no reaction. NR stands for no reaction. Essentially because the stuff you already have is super excited to be exactly where it is. It's already exactly where it wants to be. It's not changing. Why would it do that? You already had smiley faces. Why would you go to something else? We're not going to move to frowny faces. So I understand that this is a really simplistic view, and that I have not talked about how things would actually transfer electrons. I have not defined oxidation and reduction. You are missing a lot of content. But the question I was trying to answer is, somebody had asked in the submitted questions, what's the question people miss the most? And it's how to use the activity series. We usually only do 1, maybe 2 questions with the activity series. So it is not the majority of the exam. But this is a thing that we will ask. We will give you the activity series and we will ask you something like, which of the following produces products, or which of the following would you expect to not have any reaction? So the examples that I did are things that we typically ask. And so I'm trying to do it in a simplistic way because, yeah, I can't actually cover 50 minutes of content in 15 minutes. Shocker, I know. I've got about 5 minutes left. Any questions?
Nope, there's no questions here.
Cool. So what I'm just going to do to try to wrap this up nice and neatly is to remind y'all of some stuff I did not get a chance to talk about. So stuff I did not talk about that were on my list if I had time was to do more general redox stuff. I skipped all of that. I did no titrations. Titrations are on your exam. They are in chapter 9. I didn't do them. Don't have enough time to do this. So I'm going to rely on y'all to go ahead and check out those pre-recorded lecture videos. Dr. Wong does do a titration. So you are responsible for titrations. Those are in chapter 9. I had also grabbed chapter 10 example. Dr. Wong, it's me. I did chapter 10. I have something that's ridiculously similar to this in the chapter 10 pre-recorded lecture videos. Just in case you're curious, the pre-recorded lecture videos for chapter 10 are actually numbered by the section they are in the textbook. So 10.1, 10.2, and 10.3 are the sections in your textbook, and the pre-recorded lecture videos are 10-1, 10-2, and 10-3, because I actually did those by textbook section, which I think is the first time we bothered to do it that way. But thermodynamics is something that is covered on your exam, so you do need to be familiar with exothermic reactions, endothermic reactions, what those words actually mean, basics of the joule, things like that, and how to do questions like how much energy is released or required for 10 grams of methane to be consumed, as shown below. I got 4 minutes. I think I can do this question in 4 minutes. Oh, but only if one note cooperates. Uh-oh. Uh-oh. Hold on. I can do this. Come back. So I will do just this one example, just so that y'all can see, hey, chapter 10, totally on this exam, chapter 10. So how much energy is released or required for 10 grams of methane to be consumed is shown below. We are going to assume that this is in an excess. We're not given any information about the other reactant. We're going to assume it's in an excess of oxygen. Oftentimes when we combust things, we often combust in the air around us. So having an excess of oxygen is often kind of assumed. Oh, I was supposed to also draw in my delta sign, delta H. So what this is so delta H is my change in enthalpy. Change in enthalpy. What I'm going to do for this reaction is I'm actually going to treat that like it was a stoichiometric factor. So I have 10 grams of methane, which is my CH4. What I'm going to do is this number is in moles. It also has a negative sign. So what I'm going to do is my 10 grams of methane in 10 grams, so I'm going to go 2 moles. That is where I'm going to go. And I do need to balance this quickly. This is a 2, because I did not do that before I started. This one, frankly, should have been balanced for you before we actually even got in here. Okay, there we go. So here's my 10 grams of methane. I've got 16.042 grams of methane in 1 mole of methane. Here's the magic. In 1 mole of methane, I have 1 reaction, the whole shebang. Like, that's my stoichiometric coefficient for this entire reaction. And in 1 reaction, I get 890.8 kilojoules. I'm going to leave the negative sign in there to show you something. So then I can go ahead and do this math. And then we're going to flip out over the negative sign. We won't really flip out. We'll just address the negative sign. Because this is technically 1 mole of reaction. So this is 1 mole of reaction. So this is still kilojoules per mole. The number I get is 555. I'm going to do 3 sig figs just like your exam would. Kilojoules. There's a negative sign if I was carrying it all the way through. This negative sign means that it's released. So typically this question would just be 555 kilojoules released. There was a time when we did positive and negative signs in energy. It was back in chapter 3. And there was a time when we drew things that looked like this. And we said when an electron was moving from an n equals 3 to an n equals 1, that energy was released. And that when our change in energy was released, that meant that our change should be negative. Guess what? That idea is back. The negative sign means that the energy is released. That would be an exothermic reaction. Exo for exit, for leaving, for the energy getting out. And that was part of chapter 10. Not everything you need for the exam, but a kind of a ridiculously fast version, just to get a little bit of exposure to that before 6 p.m. Anything else I can answer now that I introduced a whole nother chapter in 4 minutes?
Nope.
Cool. So those actually were all the topics that I came prepared to talk about. I realize I skipped over titrations, but nobody asked me about titrations, and I just had it on the list to remind you that you are responsible for them. But otherwise, I'll scroll back up again one more time to show you that list of stuff that you are responsible for on your exam. There they all are. Your exam is again Saturday, November 13th. So in about 6-7 days, depending on how you count them, at 10 o'clock in the morning. Everybody, good luck on your exam. Do study and practice. This tends to have a lot of calculations and a lot of different topic kind of sounding things due to the nature of talking about acids and bases and redox reactions and precipitation reactions. So you do need to practice those end of chapter questions if at all possible. Good luck.